In calculus, in addition to algebra, you need to know the basics of trigonometry. So we'll do a quick review here of trigonometry for calculus, and we will start with right triangle trigonometry. Well, as you might expect, we begin with a right triangle. And here is a right triangle. And we'll mark the angle here at the left as t. And we are going to be talking from the point of view of this angle, from the point of view of angle t. You see what I mean here in just a moment. From the point of view of angle t, this side over here on the right is referred to as the opposite side, and I'll abbreviate that with OPP. The side here on the bottom, one of the legs of this right triangle, is referred to as the adjacent side, and I'll abbreviate that with ADJ. And this long side in every right triangle, the side opposite the right angle, is referred to as the hypotenuse. I'll abbreviate it as HYP. Then with respect to those three sides, there are only 6 possible ratios that you can make of these three numbers. They have been given names. Those names are the following. The sine of the angle t, that's the way that is denoted, will be defined to be the ratio opposite over hypotenuse. The cosine of t will be defined to be the adjacent over the hypotenuse. So there's 2 of them. Let's go a little further. The tangent of t is defined to be the opposite over the adjacent, and the cotangent of t is defined to be the adjacent over the opposite. So there's 2 more. I said there were 6. The secant of t is defined to be the hypotenuse over the adjacent, and the cosecant of t is defined to be the hypotenuse over the opposite. Those are the only 6 possible ratios of these 3 numbers which represent the lengths of these sides. And they are given these historical names, and these are called the 6 trigonometric functions. Now, on the coordinate plane, which is where we operate after all, how would we interpret these right triangle functions? Well, first thing we need to do is draw ourselves a circle, and we'll show how this fits in here. Draw the coordinate axes through the center of that circle, and then we'll imagine that what we're doing is we're taking those right triangles and placing them in this orientation, with this angle t emanating from the origin, and putting the right triangle here with the upper vertex here just touching the circle. One other note that we will make: in order to make this standardized, we will assume that the length of the hypotenuse is 1. That will make things easier. Now, as you recall from the previous page, the sine of t was defined to be the opposite here over the hypotenuse. But the hypotenuse is just 1, so the opposite actually represents the sine of the angle. And so this is actually sine of t. Likewise, the cosine of t was defined to be the adjacent, which is this side, over the hypotenuse, which again is 1, which means that this side here has length exactly equal to cosine of t. So you see the advantage of having the hypotenuse be equal to 1. So that means this point here has coordinates cosine of t, sine of t. And now we are in the coordinate system that we are used to. This circle here, since it has radius 1 as is centered at the origin, is called, of course, the unit circle. And just as a note, the circumference of this circle, we'll use this in just a minute, the circumference of this circle is equal to what? Well, circumference, you may recall, is 2 pi times the radius of the circle, 2 pi r. The radius is 1, so the circumference, that is the length around, is exactly a length of 2 pi units. Let's observe one other thing in this picture, that we can reinterpret the tangent, for example, differently from what we did on the previous page. The previous page, we said the tangent was the opposite over the adjacent. Well, notice that the opposite is the sine and the adjacent is the cosine, so that means the tangent can be interpreted as the sine over the cosine. That will be very handy. Likewise, the cotangent can be interpreted as the cosine over the sine. And then the other 2 functions, the secant of t can be interpreted as 1 over the cosine of t, and the cosecant of t can be interpreted as 1 over the sine of t. Now, what's the advantage to all of this? Well, everything is written in terms of sine and cosine. So if we learn everything we can about these two functions, we'll be able to calculate all the other trigonometric functions. Now, before we go any further, let's talk about how we measure angle size. Because there are two measurements that are common, one of which we will abandon for the most part. So, if we are again looking at our picture, here is our unit circle. Here are the axes running through it. Here is the angle T here. And here I'll mark the hypotenuse is 1 again. This angle here, in the kind of measurements you may have seen before now, this angle was measured perhaps in degree measure. Degree measure is an old measure that we've inherited from the Babylonians, and it is not something that we want to use for us as we proceed toward calculus. So we need a new measure. What we will do is we will say the measure of the angle is the measure of this arc, which is cut by this angle, as long as the circle is the unit circle, and the angle is starting here from the center. So what that means is, if you imagine an angle going all the way around here to the left, that would be a 180-degree angle, the angle going from here to here. That would be in degree measure. What would it be in this measure here of arc? Well, we'd need to know the arc of half the circle. But wait, we just figured out that the circumference of the circle, the whole circle is 2 pi, so this half must be a length pi, which means we've just come up with the strange equation that 180 degrees equals pi. This angle measured as 180 degrees is also the angle measured as pi. So we need to write that down somewhere. Let's write that down here. Pi, and when we have units that are measured in terms of the arc length of the circle, we will use the word radians. So pi radians is equal to 180 degrees. That is the key equation that you need to remember about angle measure and translating between the two common measures. So if you remember this, you'll be able to work forward. For example, if I want to know something in radians, first of all, let me find what 1 radian is. How would I get 1 radian? Well, I'd divide by pi. I'd get 1 radian. That means 1 radian would be 180 over pi degrees. Likewise, if I want 1 degree, I would divide the right-hand side by 180, and so I would have pi over 180 radians. So now I have a way of going from radians to degrees and degrees to radians. Just that simple. All right. With that in mind, let's look at some familiar angles so we can see how they look in both forms and then maybe learn some properties of them. Familiar angles. Well, there are some angles I know you're familiar with, like 90 degrees, 60 degrees, 45 degrees, and 30 degrees. What will those be in terms of radians? Well, if 180 degrees is pi, 90 degrees must be pi over 2. Likewise, 60 degrees is pi over 3, 45 degrees is pi over 4, and 30 degrees is pi over 6. So there are some of the familiar angles written in radian format, and you should learn the radians because that's what we will use throughout calculus. Now, there are ways to remember the trigonometric functions of some of these, and let me give you 2 pictures that I think will help. Draw yourself a right triangle in which the legs are both of length 1. Of course, that makes the hypotenuse of length square root of 2. If this is a triangle with length 1 legs, then that means the 2 angles here are the same, and they're both pi over 4. You might call them 45-degree angles. That means immediately, by looking at this picture, which is easy to draw, I can see that the sine of pi over 4, which is the opposite over the hypotenuse, is going to be 1 over the square root of 2. But that's the same thing as the adjacent over the hypotenuse, so I've learned that the sine and the cosine of pi over 4 are the same thing, 1 over square root of 2. And so on. You can do all the other trig functions based on this simple picture if you're interested in the angle pi over 4. What about other angles? Well, not all of them have nice pictures, but here's another one that does. Suppose we take what you might think of as the 30-60 90 triangle, which would be pi over 6 here for 30 degrees, pi over 3 for 60 degrees. And I recommend that you memorize one fact about this triangle, one trigonometric fact, which is that the sine of pi over 6 is equal to 1/2. That's one fact to memorize. That means that here's pi over 6, it's opposite over hypotenuse. So 1/2 is the sine of pi over 6. Now that makes this third side equal to the square root of 3. You can check that with the Pythagorean theorem. So with that information, you can go ahead and write down other trigonometric functions evaluated at these angles. For example, the cosine of pi over 6 is the adjacent over the hypotenuse. That will be square root of 3 over 2. But notice if you look at it from the point of view of this pi over 3 angle, it is the opposite over the hypotenuse, which means that that's also equal to the sine of pi over 3, and so on. You can get all the other trigonometric angles, the two angles here, pi over 3 and pi over 6, and all the trigonometric functions of those angles just by looking at this picture. So that's a handy device. With the trigonometric functions defined, we can now look at their graphs in the coordinate system. Now, I won't draw all 6 graphs. What I will do is give you a selection of ones that are of particular interest. Now, you know that everything's written in terms of sine and cosine, so really I only need to give those 2, but I will do 2 more just to make things clear, I hope. First of all, let's start with y equals sine of x. And you may notice I've switched to the letter x. I've abandoned using t here for the angle, because when we graph our functions in the xy system, we have x and y as our variables. The graph of the sine function looks something like this. It is a graph that goes no lower than -1 ever, never higher than 1. It will oscillate in this fashion forever in both directions, left and right. It crosses here at 0, of course. The peak here is at pi over 2. That's where the sine is equal to 1. And it goes to 0 at pi. Then it gets its lowest point here at minus pi over 2, and then this is minus pi, and so on. And so its period, which is the time in which, if you go from left to right, the time or the length in which it covers all of its various behaviors, from 0 down to -1 and back up again, is 2 pi. So it has a period of 2 pi. I guess I could write that down. That doesn't hurt. All right, what about the next function that I'm going to look at? Well, let's look at the cosine function, because it too is another very familiar function. The cosine function is really just a shifted version of the sine function, which makes it easy to remember. In the cosine function, the hump is on the y-axis like that. So it goes up to 1 here, goes down to -1, continues in both directions, oscillates up and down like this, crosses back here at minus pi over 2, is 0 at pi over 2, has its lowest point at pi, of course its highest point at 0, and this last point is 3 pi over 2. This is y equal the cosine of x, and this function also has period 2 pi, because all you've done is taken the sine function, which you should verify for yourself, and just shift it. If you take this hump, say, and move it to the left, you've got yourself the cosine function. 2 very familiar functions. Now, let's look at 2 functions that are not bound vertically by -1 and 1. Let's look at this function, which will be the tangent function. So this will be y equals the tangent of x, which, remember, is sine of x over cosine of x. So this is a quotient, so wherever the bottom is 0, wherever the cosine went to 0, this function will be undefined. And what happens is that at such points, we get vertical asymptotes for this function. It is undefined here at pi over 2, here at minus pi over 2. In between, if you graph it, the function looks something like this. And it goes down to -infinity and up to infinity. So it's not bound by -1 and 1. And it has these funny little breaks. And then if you go another distance, and this distance here is a distance pi, which means the period of this function is pi, unlike the other 2 functions. And if you go that distance left and right, the function just repeats, like so. So this is a function that has breaks in it at regular places because it's periodic and looks very different from sine and cosine, but is derived from them. Finally, let's go ahead and take a look at one more function. This will be y equals secant of x, which you may recall is 1 over cosine of x. So again, wherever cosine is 0, this function will be undefined. And the way I like to draw this function is as follows. Since it is 1 over cosine of x, dot in the cosine function for ways in both directions, like so. So that means this will be 1, this will be a depth of minus 1. And then wherever the cosine is 0, the secant function will be undefined, so you can draw a vertical asymptote there. And there are many of them, of course. It's periodic. And then the secant function is just a hump on top of each one of the cosine humps, going down for these ones below and going up for the one above. And that is the secant function. It is in pieces also, just as the tangent function was in pieces. It is divided up according to these regions here. And it takes 2 of these to get the whole picture of the secant function. And that is the same length as the period here of the cosine function. So the period of the secant function is, in fact, 2 pi. You should check the other 2 functions on your own to see that they have graphs that are built upon the functions they are built from. When you study trigonometry, you may have run across what are called trigonometric identities. And you may remember that there are a lot of them. And in fact, there are a lot of them. But what do you really need for calculus? Certainly a first course in calculus. These are the ones, and I call them the handy trigonometric identities. First, once again, let me draw the unit circle here. And I will show you some facts that are easy to remember. Suppose we have our angle here, t, as we've seen before. And remember that the coordinates of this point are cosine of t, sine of t, where the x distance here is cosine of t and the y distance here is the sine of t. Now, suppose we ask the question, instead of looking at this angle t, let's look at the angle minus t. So, suppose we have an angle here minus t, and continue this down. This would be the angle minus t. The coordinates of this point, of course, are easy to find because they, again, it's the cosine and the sine. So this will be the cosine of minus t, and this will be the sine of minus t. Now, what have we learned from that? Nothing yet. But look at what we have. I can rewrite these coordinates. Notice that the cosine of minus t is this x distance, and that it is the same x distance as the cosine of t. So the cosine of minus t and the cosine of t are the same thing. That's part of the identity here. The other part is, what is the sine of minus t? Well, the sine of t is this vertical positive distance. The sine of minus t is the same distance, but it's now negative. So this is negative the sine of t. And that's the other identity. So here is the first identity, and by showing that cosine of minus t is equal to cosine t, realize that this says that cosine is an even function. And since the sine of minus t is negative the sine of t, this says that sine is an odd function. So we have learned the nice identities that the cosine of minus t is the same as the cosine of t. No work needs to be done there. And with the sine of minus t, not much. You just realize that the minus comes out front. That will turn out to be very useful later. Also, if we pull out that triangle that was inside the picture a moment ago, that's this triangle where this is t, and this is the hypotenuse of 1. This vertical length is the sine of t, and the horizontal is the cosine of t. Since this is a right triangle, the Pythagorean theorem applies. Well, that leads us straight to the following 3 identities. Get 3 for the price of 1. These are called the Pythagorean theorem identities. And they're easy to remember because you just look at this picture. In this picture, the Pythagorean theorem says that the sine squared plus the cosine squared must equal 1 squared. In other words, you have this famous identity, and I'll write it this way to be very careful. The sine of t quantity squared plus the cosine of t quantity squared is equal to 1 squared, which is just 1. That is the most famous identity in trigonometry, and you will use it again and again. Sine squared plus cosine squared equals 1. But you get 2 free identities from this. If you, in this first step, if you divide by cosine of t squared, what happens? Sine t squared over cosine t squared gives you tangent of t squared. Dividing this second piece by cosine t squared, of course, gives you 1. And then 1 over cosine squared is going to give you secant squared. So secant of t squared. And there you have a second identity. Also very handy, relates tangent and secant, just as this one related sine and cosine. And one more time, if we come from the beginning here, and instead of dividing by cosine squared, we divide by sine squared, the other possibility, what happens? Well, sine squared over sine squared gives me 1. Cosine over sine is going to give me cotangent squared. And then 1 over sine gives me the cosecant squared. So we've just come up with 3 different identities, all based on 1, all in turn based on the Pythagorean theorem. And that will be the last identity we do for this section. In many applications of calculus, such as in physics or in engineering, when you work with trigonometry, sometimes you need to be able to so-called solve for triangles. Well, that involves the use of the laws of sine and cosine very often. So let's go ahead and talk about these. So these are results that are often used in applications. The first one that I will mention here is the law of sines. And what's advantageous about both of these laws is that they don't depend upon having a right triangle. You can apply this to any triangle. So for example, let me draw something here that looks kind of irregular. This is meant to represent any triangle. And let's label the various parts. Let's call this angle A, capital A, capital B, and capital C, these angles. The side opposite angle A is usually labeled with a small a, opposite B with a small b, and opposite C with a small c, although it's sometimes hard to tell the big and the small c apart. What is the law of sines then? The law of sines simply says that if you take and evaluate the sine of angle A and you put it over the length A, that ratio will be the same thing as the sine of angle B over the length B, and that's the same thing as the sine of angle C over the length C. This is the law of sines. These ratios are all equal. So if you take a pair of them like this first pair, if you know 3 of these facts, you can get the 4th one. And that's what these are used for in solving triangles. Now what about the law of cosines? The law of cosines is very nice because it extends the Pythagorean theorem from right triangles to non-right triangles. Again, let me draw that sort of typical triangle here so we can have it to refer to. This would be angle A, B, and C, and then little a, little b, and little c. And here's what the law of sines says. And there are 3 forms of it, and you'll see why. It just, since A, B, and C, there's nothing special about any one of them. Unlike in a right triangle, remember, where we usually let C be the hypotenuse, here the A, B, and C are just any of the sides. So c squared equals a squared plus b squared, which sounds exactly like the Pythagorean theorem, except because this isn't right, we have this adjustment factor, minus 2ab times the cosine of c. This can also be written this way. B squared equals a squared plus c squared minus 2ac. Now you notice where the factors are coming from here. A and c are the 2 factors on this side, the 2 terms here. A, B were from the 2 squared terms here. And then this should be the cosine of the angle corresponding to the side here. That's cosine B. And finally, there's a squared equals b squared plus c squared minus 2bc cosine of a. And this part over here is an adjustment. Or if you like, a fudge factor for non-right triangles. So now you've seen two sets of laws, the law of cosines and the law of sines, which can be used on triangles which are not right and which will help you in applications. As a last note on trigonometry, and again something that's useful in applications, we'll talk about some trigonometric families. Here are the two families we'll discuss. The family that's of the form y equals a, some constant, times sine of bx, where b is a constant. We'll also look at the same thing for cosine, so a cosine of bx. So the actual families will have the forms here I am boxing in. These occur a lot in practice. Now let's recall a couple of things before we go any further. That just looking at these as functions with a constant out front and a constant inside, we already know what these letters, these constants, are going to do to the functions. A is going to be a measure of the vertical stretch or compression of the graph of the function. And B, since it is on the inside, will measure the horizontal stretch or compression of the function. And just for the record, since we'll use this in a moment, notice that sine and cosine have the same period, so 2 pi is the period of both of them. Period of both sine and cosine. Now, in this environment where we're talking about trigonometric families, we want to interpret the a and the b in a different way. In this environment where these functions, remember they had waves, they represented waves. In this environment, the absolute value of the a will represent what's called the amplitude of the function. That is how high and low it goes. If you take the period 2 pi and you divide by the absolute value of b, what is multiplied by the x here, that will give you the period of this family of functions. Now that's opposed to the period of sine and cosine alone. The period of the functions where there's a b factor here will give you the period of the family. Now of course as b is 1, we're back to the original period. And then if you flip the period over, the period absolute value of b over 2 pi, which is 1 over the period, that gives you a piece of information referred to in physics as the frequency. And these are things that you will see over time, so it's good to know what their definitions are. There are two other versions of this, two other families. For y equal a times sine, and now let's introduce bx minus c, so we've introduced a constant there, or y equals a times cosine of bx minus c. So these now are the new families. And all that's new about them is that there's a c in here now. The way to read these is first to rewrite them, and then you can go ahead and interpret them based on what we've already seen. If you rewrite these, y equals a times sine, and we'll factor the b out here, b times x minus c over b. And the other one is the same. I won't write it out. That's similar. Now look what we have here. We have a times sine of b times the variable expression, and all this is a shifted version of the function that was on the previous page. It is shifted c over b. So this is, and in both cases it will be the same, this is just a horizontally translated graph of, in this particular case, y equal a sine bx with no c involved. And that you're translating by c over b, whatever it is, plus or minus. And so that would be a translation left or right. So if you interpret this, you see that we already have all the information we know to interpret these two families. And that's all we'll say about trigonometry, and get on to calculus. Soon we'll be looking at exponential and logarithmic functions. But before we get there, let's talk about the idea of an inverse function. We'll start by asking ourselves, what does it mean for a function to be inverse to another function? Well, the idea that's trying to be mathematically encapsulated here is, when do we have the situation when two functions undo each other? And let me give you a picture to suggest what I'm talking about. Suppose we start with x, the domain element, and we apply a function f to it and result in a range element, or an image, f of x. What if we want to undo this function? If we want to undo it and we actually produce a function in the process, a backwards function, we'll call that function the inverse function. Now, sometimes you can't undo a function. Sometimes you have difficulty depending on what the function is. So inverses will not always exist, but when they do exist, they're very nice. They allow you to quickly undo something that you have previously done. Let me give you an example to illustrate a situation where this works. Suppose we have a function that takes x to x cubed plus 1, and that will be our y value. So what does this function do? Well, if we put it into words, the first thing it does to x is it cubes x, and then it adds 1. So cube then add 1 is what this function is actually doing. Now let's ask ourselves, what would we want an inverse function to do? We would want an inverse function to undo this. So an inverse function ought to do the following. It ought to, first of all, reverse this process. Instead of adding 1 as the last thing, we want to first subtract 1. And then we need to undo the cube. So subtract 1 and then uncube. So if we were going backwards, the function that would take us backwards would be the function that takes y here to, starting with y, subtracting 1, and then uncube means take the cube root. So we have discovered now the inverse function here. This function does have an inverse, as it turns out. The original function was x cubed plus 1. The inverse function is the cube root of y minus 1. But you want to think of it as an operation, a sequence of operations that is then undone by going backwards. This is the situation we want to explore a little bit more here. So first, we need a definition and a notation. So we write, when such a thing exists, the function inverse to a given function, and remember, of course, as I just said, it may not exist, but when it does exist, all right, provided it exists to be sure here, provided it exists, we'll write that function as f inverse. Now, what I've read here is f inverse. You may look at this and say, it looks like f to the minus 1 power. And you're right, that's exactly what it looks like. But the way we read this is f inverse. And this is definitely not the minus 1 power. This is an inverse. All right. Here is a definition that will tell me when I have an inverse. The functions f and f inverse are really inverses, provided we have two things happen. Provided both, when you take f inverse of f of x, you get back x. And that has to work for all x in the domain of the function f. And it has to go in the other direction. See, in this one, you start with x, you apply f, and then you undo it via the inverse. But the other direction has to also work. F of f inverse of x must equal x, and that's for all x in the domain of the starting place, f inverse. See, in the first one, the x's here start out in the domain of f, f applies to them, and then f inverse undoes that and produces the original value. Here, the x's are starting off in the domain of f inverse acts on them, and then f undoes that. So these two functions undo each other, and that is the key property that makes them inverses. We're going to see this when we look at exponential and log functions as sort of the classic cases of inverse. Now, to connect up the domains and the ranges, let me draw my picture once again. Here's the function that takes f to f of x. Here now we're assuming there's an inverse. So f inverse takes f to, well, let's see, it would be f inverse of f of x. And if it's an inverse, these have to be equal. So since that's true, when we look at this, we say, what is the domain of the inverse function? Well, the inverse function starts here, which is the range of the original function. So the domain of the inverse function is the range of the original, and likewise the range of the inverse function over here is the domain of the original. So that is the relationship between their domains and ranges. And as we look at more examples, you'll get a better sense of how inverses work, and we'll look at their pictures too. We just defined what it means for a function to be inverse to another function, but we did raise the question that sometimes an inverse may not exist. So we'd like to know, when do functions have inverses? So when do inverse functions and their graphs exist? Well, we'll start right out by writing a theorem down. And the theorem is what you want to remember to be able to answer this question, when does a function have an inverse? So a function has an inverse is the first statement. That will happen if and only if, that's what this double arrow means again, if and only if it is a so-called one-to-one function. And I'll give you a quick definition of that. A function is one-to-one if it has the following property. If two x values are different, if x1 is not equal to x2, then the f of x values are also different. So if the x values are different, they go to different places. That makes a function one-to-one. Now graphically, there's an easier way to tell. A function has an inverse if and only if it is one-to-one, if and only if, again, its graph intersects any horizontal line at most once. So if you draw horizontal lines on a graph of a function and you only hit the function once at most, or you might hit it no times at all, then that function will have an inverse. This last test, by the way, this is referred to as the horizontal line test. And you can compare that with the vertical line test, which tested whether something was a function at all. This tests whether a function is one-to-one, or if you like, whether a function has an inverse, which is what we're really interested in. Now, in particular, there are a large class of functions that are one-to-one that you should know about. Increasing and decreasing functions. So increasing and decreasing functions, you'll see in a minute why I'm writing it this way, have inverses. So if you have functions that are increasing or decreasing, they are guaranteed to have inverses. Why? Well, here's the definition of an increasing function. If x1 is less than x2, so you're moving from x1 to x2, the function's graph should go up. So that means that f of x1 should be likewise less than f of x2. And the picture makes that clear. If this is x1, which is certainly less than x2, then the picture you want to go up, and that's reflected by this statement. Well, if x1 is less than x2, they're different, so different points are going to different functional values, which is exactly the definition of one-to-one, and so increasing functions have inverses. Likewise, decreasing functions, if x1 is less than x2 as you move from left to right, then you want the function to go down. So you want f of x1 to be less than, greater than. I said go down, so greater than f of x2. And you can't go wrong if you draw yourself a picture, even if you say it wrong. x1 less than x2, as you move from left to right, you want to go down. So the f of x1 here should be bigger than the f of x2 here. So we correct that. So increasing and decreasing functions are large classes of functions that you will encounter that definitely have inverses. Now what about graphing an inverse function? How hard is that? Well, if you know the original function, it's not hard at all. Graphing an inverse function. And here is the reason. If you have a point, say x, f of x, and that point is on the graph of the original function f. So you've got little x here, which is going under f to f of x. Then, the point where you simply switch the order, where the f of x becomes the first value and the x becomes the second, that point is on the graph of the inverse function. And the reason is because what does this say? This says that f of x is where you start, you apply the function, which is f inverse in this case, and you end up with x, which of course is exactly what you get when you take f inverse of f of x. So that is exactly right, which means you just need to reverse the order of these two. Now when will these not change? These will not change when the two numbers on either side are the same. But if you have x and x, that means you have the line where the y value is always x. That's the 45-degree line. That is going to be the place we can reflect over. Now we're going to see how the graphs of those functions are related. So the graphs of f, the original function, and f inverse, its inverse, are related in the following way. They are reflections, as in a mirror, across the y equals x line. That will be the mirror for the purposes of this reflection. So let me give you an example. And here is my coordinate system. Let me dot in the 45-degree line here, which will be our mirror. And let me graph the cubic curve, which goes something like this. So let me mark this here. This is y equals x cubed. And that function is increasing from left to right, so it is certainly a function that has an inverse. And let's ask the question, what would the inverse of this function look like? Now we happen to know what it is. It is the cube root function. But even if we didn't know it, we could draw its graph by saying it's got to be the reflection of this graph through this 45-degree line, which means it has to look something like this, which means this function here must be the graph of x to the 1/3, or if you like, the cube root function. So the two functions have their graphs being reflections through the 45-degree line. So if you know the original function's graph, even if you don't know a formula for the inverse function, you can at least get a picture of what its graph looks like. Although the most familiar sorts of inverse functions we will be looking at will be the exponential and logarithmic functions, there are cases involving what are called the inverse trigonometric functions that we want to talk about. And to start this out, let me say something provocative, that the trigonometric functions don't have inverses, which would seem to make this section superfluous. So I need to explain what is usually meant by saying inverse trigonometric functions. So we'll do that by starting with the sine function here. And let's look at its picture and see where I'm going to go with this. Now the sine function has a graph that looks something like this. It goes up to 1, down to -1. Over here on the right has a peak at pi over 2. At the left it goes lowest at minus pi over 2, and so on. And the first thing you should note is that because of the horizontal line test, this function cannot have an inverse. The horizontal line test, remember, says that if you draw a horizontal line, you should not be able to strike the curve more than once. Well, you can strike this hump, for example, twice, and in fact, if you continue with that horizontal line, will strike the sine curve infinitely many times. So the sine curve doesn't have an inverse. So what do people mean when they talk about inverse trig functions? Well, what they mean is that you take the sine function and you restrict it to a piece that does have an inverse. For example, if you take this piece from here to here, where you start at the lowest point and go to the highest, there's no problem. It's a nice increasing piece, and that's going to have an inverse. As long as you don't go over the hump in either direction, you're guaranteed of an inverse. So that's what we will do. And what I will do is draw the graph of the inverse by taking this little piece and reflecting it across the y equals x line here. And that will be what is meant by the inverse sine function. So that's what people mean when they say this. So come on over here and let's look at the graph. Here's the way to get this set up. The x values here went from minus pi over 2 here to pi over 2 here. So those will now be the y values. And the y values here went from minus 1 to 1, and those will now be the x values. And there will be a point at each corner, and the curve went like this before we reflect it, and once we reflect it, it's going to have a curve that looks something like this. So there's my minus 1 mark there. The curve starts and ends with these dots. It does not continue. It's not periodic. It is a curve that is strictly limited because of where it came from. It's a limited sine function, so it's going to be a limited picture here. Let's talk about the notation used to represent this function. It is sometimes written sine inverse of x like this. It is also written arc sine of x. That's an older notation, but it's advantageous because it has no superscript. On calculators and sometimes computer programs, you'll find it as a sine x very often. But in every case, it is not equal to 1 over sine x. This means inverse. It does not mean reciprocal. Be careful that you don't make this mistake. All right, that is the sine function. What about the cosine function? Can we do the same sort of thing? Of course we can. Let's find the same argument. Now the cosine function looks like this and goes off in both directions. This, of course, is happening at 0. This is at pi over 2. This is happening at pi, and so on. Now, based on what we saw previously with the sine function, what we're going to want to do is take the piece that goes from here to here, this decreasing piece, and take that as the part that we will restrict the cosine function to, and then reflect across the 45-degree line here to get the inverse function. So that's what we'll do. We'll come over here and we will create the cosine inverse function, which will look something like this. Here the x values went from 0 to pi. Those are now going to be the y value domain. The y values here, of course, went from minus 1 to 1, just as before. And so the x values here will go from minus 1 to 1. And when you take this piece of the curve and reflect it, you're going to get something that looks like this. And that is a picture of the inverse cosine. Again, for notation, sometimes people write it as cosine inverse or arc cosine of x, or they'll write a cosine of x for convenience on a calculator or computer. But in every case, remember, this is not equal to 1 over the cosine of x. That simply is not true. This symbol, again, means inverse. It does not mean reciprocal. All right. Well, I won't do all 6 of these functions. What I will do is 2, or rather 1 more, to get you a sense of what this is like. Let's take the tangent function. Now, this has a particularly nice inverse, so this is worth doing. And to avoid hitting the tangent function more than once, we will have to limit ourselves, just as we limited it ourselves in the other cases, to a function that has a piece that is increasing. Now, if I put the other pieces in here, the horizontal line test would be violated because any horizontal line would strike the curve in many places. So we can only take this single piece. And if we reflect it across the 45-degree line here, you will see that what we get is a nice function that's useful for all sorts of examples later in this course. It will go no higher than pi over 2, and it will go no lower than minus pi over 2. And those will be asymptotes just as they are here from left to right. They're now up and down asymptotes. And the function from below to above went from minus infinity to infinity, so there were no restrictions in this direction. So there are no restrictions here. And if we flip this, we end up with a curve that looks something like this. So this is a very nice curve that is defined for all real numbers left and right, and yet is bound on the bottom by minus pi over 2 and on the top by pi over 2. This will turn out to be very useful. Again, here's the notation, tangent inverse of x, also written arc tangent of x, also written a tangent of x. And of course, as I've mentioned before, this is not the same thing as 1 over tangent of x, because this symbol means inverse and not reciprocal. You should try the others to see what they're like, but really these three inverse trig functions are the ones that are going to be most useful to you and the ones you'll encounter most often. Now let's say a couple more things. How do you read something like this? Suppose I have y equals sine inverse of x. Now this will work for the other inverse trig functions also. What you want to do is read this as the following. This is the angle whose sine value is x. Now that's a phrase you want to get into your head when you see this. You want to say y, or sine inverse of x, is the angle whose sine is equal to x. Meaning, that means the sine of y is equal to x. This turns out to be very helpful in examples like this. If someone gives you this problem and says, simplify the following, the tangent of sine inverse of x. Now this looks complicated and it looks unexpected. But if you remember that sine inverse of x is a representation of an angle, this makes perfect sense. Now how would you make sense of this? Well, the key is that if sine inverse of x is the angle whose sine is x, you know more about this angle than you normally know about angles. You know its sine value. So if you just, for the solution here, if you just construct yourself a right triangle and mark this angle as sine inverse of x, because that's the name of an angle after all, and remember that's the angle whose sine is equal to x, and x can be thought of as x over 1, that's opposite over hypotenuse. You now have two sides of a right triangle. You can easily from that get the third side. That'll be the square root of 1 minus x squared. And then from that, you can immediately write down what the tangent of sine inverse is, because you want to know the tangent of this angle. That's the opposite over the adjacent. And so that will be equal to x over the square root of 1 minus x squared. So you've just simplified this complicated looking expression by understanding that the sine inverse really represents an angle, and so we can interpret it in the way we've interpreted angles before, in a right triangle. As our last step in this review of pre-calculus, let's go ahead and look at exponential and logarithmic functions, and we'll start by looking at the exponential function family. The exponential function family has the following form. F of x equals b to the x. This is what they all look like. Now we have to put some conditions on b. B is a constant here. This is where b is a positive number only, and where b is not equal to 1. Of course, if b is equal to 1, it's very uninteresting. 1 to any power is 1. And we want to keep b greater than 0 so we don't start generating complex numbers. So b is greater than 0, b not equal to 1. And b is what's called the base, b for base, of this exponential. Another note that can be made here is that the domain of this function is all real numbers. We will be able to take any positive base that's not equal to 1 to any power whatsoever. That's not only the rational powers or the integer powers we've seen before, but also irrational powers, for example. So this will be the definition of exponential functions. And so, for example, We see things like 2 to the x, we'll see quite a bit. We can fancifully write pi to the x and various other sorts of functions. Now let's be careful. Contrast that to x squared and x to the pi. These are not exponential functions. Even though there are exponentials involved, these are not exponential functions. Exponential functions, that piece of terminology, is reserved for functions that have a base that is a constant and a power that is a variable of some kind. These down here are powers. That's what we call them instead of exponential, because the base is variable and the power is constant. So keep that straight. First, let's look at what the pictures look like of these families. Suppose y equals b to the x and b is greater than 1. Since b is not equal to 1, we've got two choices. Let's look at the greater than 1 case. If you look at the graphs of such functions, they will all look basically like this. They will all pass through 1. And why is that? Well, because b to the 0, when x is 0, which is what it is here, when x is 0, b to the 0 is always equal to 1, so the y value is always 1 there. What other possibilities are there? Well, it could be a function like that. It could be one that comes in very tightly like this, but it will always pass through that 1 point. So this is the infinite family here that's being described. Now, what if we look at y equal b to the x, but we take b greater than 0 but less than 1? In that case, the only thing that's different here is that instead of going from the far left, where it is nearly 0 but positive and growing to infinity to the right, it starts and goes the other way. So it still passes through 1 because of the same reason b to the 0 is 1, but now it starts up here at infinity and comes down here and gradually approaches 0. So there will be various versions of it like this. And you can play with this on your calculator if you like by putting in various values of b and getting a sense of what the pictures look like. But that is the two types of families that the exponential functions will fall into. Now, there happens to be a particular base which is separated out as special. It's called the natural base. Now, why it's called natural, you won't be able to see right now, although I'll give you a reason. It's the kind of thing that will turn up as we do the calculus. You'll find that for the calculus to be nice later, this is the base to use. The natural base, called, and this is a traditional letter, E, is such that, and here's the reason, although it'll make more sense later, is such that if you take the tangent at any point, x e to the x on the graph of that function y equals e to the x, of course. If you take the tangent at a point x e to the x on the graph of y equals e to the x, the tangent has slope e to the x. In other words, the second coordinate is not only the y value, it is also the slope of the tangent line at that point. That special feature makes this into the natural base. Now that doesn't seem very natural right now, but you'll see later that it really is. If you want to know what E is, E can be calculated, another thing we'll discuss later, as approximately 2.71828, etc. It is an irrational number. Might as well put that down while I'm here. It is an irrational number and will turn out to be very important. Once you have that base, the function that you create with that base is, as you might expect, called the natural exponential function. And this is a function that you will most often use in this course. Rather than the other exponential functions, you will often defer to this one, f of x equals e to the x. And there's an alternate notation. I might as well slip this in here. There's an alternate notation that is sometimes used to avoid subscript or superscripts. Sometimes people will write exp of x. Now, although that stands for just plain exponential, when it's used in this context, it always means base e. So there is an alternate notation for you, and that's the last I'll say about the exponential family right now. Next, the logarithmic function family. This family has the following general form. F of x equals log, standing for logarithm, subscript b of x. And we could put the x in parentheses if we want, but people don't do that unless there's more than one symbol there. In this case, again, we assume that the base b is greater than 0, and is not equal to 1. And again, b here is the base. You see how this is at least sounding related to the exponential. One thing to note, and we'll see this in the pictures, is that the domain of this function is not all the real numbers. You cannot take the log of all possible real numbers. You are not allowed, and you'll see why, you can't take the log of x if x is negative or if x is 0. So that leaves you with all the positive numbers as the domain. When you see an expression like log sub b of x, what you want to realize is it is a representation for the following. It is the exponent to which b, the base, must be raised to get x. Thus, what this means is that if you write y equal log base b of x, that is saying the same thing as b to the y equals x. B to this expression here equals x. This expression represents the exponent to which b must be raised to give you x. And this will become clearer as we realize the relationship between logarithmic and exponential functions. So, if you have such a b greater than 0, b not equal to 1, then, and here's that relationship, b to the x, that function, and log base b of x are inverse functions. So one function undoes the other, and that should explain something about the previous page. Let us go ahead and look at the graphs of the log function while we're here. Log base b of x. Let's take the case where b is greater than 1. And in that case, the picture looks like this. And here is 1. Here is a typical log function for this family. Now, why would it look like that? Well, remember the log function, we just said, is the inverse of the b to the x function. What was the corresponding b to the x function? Well, that looks something like this, passing through 1 here. And notice if you imagine the 45-degree line here and you flip it over, this is the curve you get. Now, depending on what b is, it could be one that looks like this, it could be one that looks more like this, and so on. But there's an infinite number of members of this family, and it passes through this point. That is to say, log base b of 1, the x value here, is equal to 0, the y value height, because b, the base, to this exponent 0 is equal to 1, which is what we knew from the exponential curves. That will apply here and to this other case. If y equals log base b of x, where b this time is between 0 and 1, then the picture for these log function graphs look basically like this, where it's crossing through 1 again for the same reason it crossed through 1 before. And why does it look like this? Well, if you remember, the original function that was the exponential looked like that, passing through 1. And if you can imagine that flipped across the 45-degree line, you see that this is what happens to it. Now, of course, depending on the value, it's going to look a little different depending on what b value you choose, but they're all going to look like this and pass through 1 here on the x-axis. So that gives you the two different pictures of the families of the logarithmic functions. Now, let's talk a little bit about notation. Since log base e of x is so important, this is the natural base, remember, we have a notation for it. Rather than log with a subscript of x, we just write ln of x, where the n in natural is where the n comes from there. This is the notation you want to use from now on for log base e of x. Continue to use that throughout the course. So now we can make some statements about e to the x and natural log of x. As inverses, we can say the following. the natural log of e to the x is equal to x. For all x, let's see, the x's would have to be in the domain of e to the x, but that's everything. So this is all x's in R. And another way to write this, if we use that alternate notation, is the natural log of exp of x is equal to x. And that may remind you of how we saw inverses work before. There was an f and an f inverse. Likewise, if you take e to the log x power, the natural log x power, you get x. For all values of x in wherever the x's come from for natural log, which is what's done first, and that's just 0 to infinity, the positive x's. And again, if you rewrite this way, you won't have this superscript business going on. You can write it as exp of natural log of x, and that equals x. So this may make you feel a little bit more like you're seeing the f inverse pattern that we've seen before. But in either case, these are going to be expressions that you're going to use a lot, especially in solving certain kinds of equations. Finally, let's take a look at solving exponential and logarithmic equations. Here are some notes that will be useful in that process. The first thing is, since, and this is a well-known formula, log base b of x can be written as the natural log of x over the natural log of b, and this is sometimes called the change of base formula because you're changing the base from b to base e. In this case, although you can do this with changing of bases between any two bases, we'll use it for natural log. Since you can always write this way, this means any log that is not base e can be written in terms of base e. So here is the recommendation that I want to give you. Whenever you do problems involving logs or exponentials, use only the natural log symbol and base e to the x symbol for calculations. Do your best to put everything in these terms, and that will bear fruit later on as we continue on with the calculus. Another piece of information that you want to recall from your past about logarithms that you will use in solving equations is this. Suppose we have some numbers here. Suppose a is greater than 0, c is greater than 0, and r is some real number. Then there are three logarithmic laws. The natural log of a product is the sum of the logs. That's handy. The natural log of a quotient is the difference of the logs. And finally, the natural log of a to some power, the power comes down out front, and you can write this as r times the natural log of a. Those three logarithmic rules will be ones that you're going to use a lot. But just to give you a little bit of flavor here, let's do one example. And we'll solve for x. This is sort of a classic example, so I like doing it. Solve for x in e to the x minus e to the minus x over 2 equals 1. I want to know what x values satisfy that equation. Well, to begin with, let's just see if we can simplify a little bit. E to the x minus e to the minus x over 2 equals 1. I can certainly multiply both sides by 2. So I'll have e to the x minus e to the minus x equals 2. And then I never like having negative powers, so let me rewrite this without that. E to the x minus 1 over e to the x equals 2. And then I would prefer not to have fractions, so let's get everything over the same denominator, or maybe eliminate this denominator. How about that? If I multiply through the entire expression, and I can write this here to keep track of this, multiply by e to the x, then what do I get? I get e to the x quantity squared minus e to the x over e to the x is 1 equals 2 times e to the x. And then if I pull everything over to the left, I have e to the x squared minus 2 times e to the x minus 1 equals 0. And the thing you want to recognize here with a little thought is this is that this is a quadratic in form. It has the form of something squared minus 2 times something minus 1 equals 0. That is a quadratic equation. Now, e to the x is here in place of that variable. So in order to use my quadratic information, let's do this. Temporarily, let's let u be e to the x. And then at the end, I'll restore this. So what do I have? I now have u squared minus 2u minus 1 equals 0. I can use the quadratic formula to then find out what u is. Let's see, I need to take negative of the coefficient of u, so that'll be 2, plus or minus the square root of this coefficient here squared, which is 4, minus 4 times a, which is 1, times c, which is a minus 1. This is all over 2 times a, which is 1. Under the square root, I have 4 plus 4, so I have 8. So this is 2 plus or minus the square root of 8 over 2. And I realize that 8 can be written as 4 times 2, and the square root of 4 is a 2 that comes out. So 2 plus or minus 2 square root of 2 over 2, well, that's nice. I get rid of all those 2's, and I end up with 1 plus or minus just the square root of 2. All right, that is u. I remember that u was equal to e to the x. So let me pull this to the other page so we can keep it all together. Then e to the x must be equal to 1 plus or minus the square root of 2. But wait a minute. E to the x, if you remember its graph, looked like this, is always positive, which means 1 minus square root of 2 cannot occur. This is e to the x is never negative. So we discard that solution, and we know that e to the x equals 1 plus square root of 2 is the only solution that can hold. Now I need to get at the x. Well, I would like to undo the e to the x function. Luckily, it has an inverse, the natural log. So the natural log of e to the x is the natural log of 1 plus the square root of 2. By definition of inverses, the natural log and the exponential function undo each other and leave us with x. So x is equal to the natural log of 1 plus the square root of 2, and that is the solution. Now, if you're really interested, this means that x is approximately equal to 0.881. But for our purposes, this answer is perfectly good, and we have solved that exponential equation. And that finishes our review of pre-calculus.